Hi, my name is Shahnawaz. In this lecture, we will introduce the notion of Hausdroff spaces. If we look at the topological space, say R, with the usual topology, then we know every singleton set in R is actually closed. So if we take A to be the singleton, say x naught, which is contained in R, then this A is closed. I mean, this A is a closure. Now, why this is true? Because if we prove the derived set of A prime is empty, then the A closure, which is A union A prime, will be actually equal to A union the empty set, which is A. So that means every singleton set in R has an empty derived set. Now, why this is true? Say let x be any real number and u be any open set in R such that this x is in U. Now, if we look at this intersection U set minus this x and take it is intersection with x naught, sorry, take it is, this is x minus x naught. I mean, we have this intersection A here, so this is going to be an empty set. That means no real number in R is a limit point of x naught. So this means this topological space is such that every singleton is a closed set. However, if we look at this topological space, say we have a set of 3 points, say A, B, C, and let us consider a topology T on X, given as it contains the open set is X, the empty set phi, the singleton B, and say say AB and BC. Then if we look at this singleton set, which is a subset of X, so this is not closed. For if it is closed, then its complement has to be open. So if we look at its complement, that is the set AC, and this AC is not an open because this AC is not in T. So this is not open means it's not closed. So that means the singleton is not closed. Now, such spaces, in such spaces, the singletons are not closed, and in these kind of spaces we have a sequence of pointers in X which converge to more than one point, and such spaces are not very interesting to study. Now, to rule out these spaces, we introduce the Hausdroff spaces. Now, let us first define the Hausdroff spaces. So we have the definition of Hausdroff spaces. So we call a topological space, say a topological space, say xt, is called a Hausdroff space, or sometimes it is called the T2 space. If for any 2 points, if for any 2 pointers, say x1 and x2 in X, with x1 is not equal to x2, I mean these 2 points are distinct, then there should exist open sets say u1 and u2 containing x1 and x2 respectively, such that they are disjoint. So we call X a Hausdroff space if any two points in X can be separated by two open sets, I mean two distinct pointers. So we have this set X here, and we have a point say x1 and x2. So if we can separate any two distinct points by the open sets, then such a space is called a Hausdroff space. Now let us give some examples of Hausdroff spaces. So consider the set of real numbers with usual topology. Then it is a Hausdroff space. So that means we have to prove any two distinct real numbers can be separated by two disjoint open sets, I mean two disjoint open intervals. So let us consider this to be our set R, and suppose we are given 2 points, say x1 and x2. So if we can separate these two pointers with the open two disjoint open intervals, then that means R is Hausdroff space. So what we do, so for the solution, take two real numbers in R which are distinct. So now x1 and x2 being distinct, so we can talk about the distance between x1 and x2, because we are having R equipped with the usual topology. So the distance between x1 and x2 is the difference of x1 minus x2, its absolute value. So if we take R to be the I mean if this is the distance between these two real numbers, and that means this is over R, this is over R. So this is R is a positive real number, because x1 and x2 are not equal. Now what do we do? So let R be the distance between these two real numbers, and we take epsilon to be less than R by 2, i.e. suppose this is R by 2 here. So this distance over here, this is R by 2 and this is R by 2. Now what we do, we take epsilon to be the less than the half of distance between these 2 points. Then what we do, so then we have x1 in the open interval, x1 minus epsilon and x1 plus epsilon. So we have this open interval here, so this is x minus epsilon, this is x plus epsilon, and we have x2 in the interval x2 plus epsilon, and sorry, x2 minus epsilon and x2 plus epsilon, such that, so if we look at the intersection of these open intervals, so such that x1 minus epsilon, x1 plus epsilon intersection with x2 minus epsilon and x2 plus epsilon is empty. So if we take u1 to be x1 minus epsilon and x1 plus epsilon, and u2 to be equal to the x2 minus epsilon and x2 plus epsilon, then we have proved that these two real numbers x1 and x2 can be separated by two disjoint neighborhoods. So then first of all, these u1 and u2 are open, so then u1 and u2 are in the usual topology, such that x1 is in u1, x2 is in u2, and u1 intersection u2 is empty. So this proves R equipped with the usual topology is actually the Hausdroff space. Now let us consider another example. So let x be a 2 points, let's say A, B, and consider the space x D, where D is the discrete topology on X. Then XD is a Hausdroff space. Now note that by discrete topology we mean the collection of all subsets of X. So we have X here, we have empty set, we have singleton A, we have singleton B. So this is the topology here. Now I mean the only two distinct points in X are A and B itself. So the only pair of distinct points in X are A and B. So if we are able to separate these 2 points by 2 distinct open sets, then X will be a Hausdroff space. So then there exists u1, say this is equal to the singleton A in the discrete space, and u2 to be equal to B in D, such that u1 intersection u2 is empty, and u1 contains A and u2 contains B. So this is again a Hausdroff space. Now let us give an example of a space which is not Hausdroff. So let X be an infinite set, and let us consider the topology, the cofinite topology on X. So consider X T COF. By COF we mean the cofinite topology or finite complement topology. So then X is not a Hausdroff space. So why this is the case? So consider, so let us first choose two distinct points in X. So let x1 and x2 be in X such that this x1 is not equal to x2. Now we know that an element in this topology is, this is open if and only if U complement is a finite set. So or X itself. So U is open with respect to the cofinite topology if either U is X or U complement is finite. So then this U is in this topology. So let U1 and U2 be open sets in X such that x1 is in U1 and x2 is in U2. So that means now U1 and U2 being open sets, this means U1 complement is finite and U2 complement is finite. So they are both finite sets. Now we claim their intersection will be empty. So we know the cofinite topology consists all subsets of X whose complement is finite and the empty set. Now U1 and U2 are non-empty because x1 is in U1 and x2 is in U2. So U1 and U2 being in this topology means their complements are finite. In other words, U1 and U2 will be infinite. So observe that U1 and U2 are infinite since they are non-empty. So we claim that U1 intersection U2 is empty. So this is our claim. Suppose not. Suppose U1 intersection U2 is non-empty. So if this is non-empty, that means so we have this is our claim, and this is our claim. So suppose this is empty. What does that mean? That will mean that U1 intersection U2. Now U1 and U2 being open sets, so their intersection is also open set. So U1 union intersection U2 is also open, and hence their complement, its complement is a finite set. But U1 intersection U2 complement is phi complement, which is X, and this X is an infinite set. So that is not the case. So this is the one way, or we can say here this is the one way, or we'll proceed like this. Now U1 and U2 being empty, so we have this X here, which is an infinite set. We have U1 here and we have U2 here. Now we suppose they are disjoint, that means this u1 is contained in the intersection of u2. So if we look at the u1 is contained in the complement of u2. So if we look at the complement of u2, that is this set, the portion, the region colored with the red lines. So this means u1 is contained in u2 complement. So now this intersection being empty means, so this implies that u1 is contained in u2 complement. Now u1 being infinite set and u2 complement being finite set is a contradiction, which is a contradiction since u2 being in t cofinite means its complement is finite. So since u2 complement is finite and u1 is infinite. Now let us prove a small result, i.e., so we have the following lemma. So this lemma states that every finite set in a Hausdroff space is closed. So note that in this example x has to be infinite. So if x is finite set and we consider the cofinite topology on x, then that topology will be equal to the discrete topology, and we know the discrete topology is always the Hausdroff. I mean the discrete topological space is the Hausdroff space. So that is why we chose here x to be an infinite set. Otherwise this cofinite topology will be equal to the discrete topology. So every finite set in a Hausdroff space is closed. So let us prove this. So what we have to prove? So let us consider first a topological space which is Hausdroff. So let xt be a Hausdroff space. So we have to prove any finite set is closed. So we'll first prove any singleton is closed. So we will first prove any single point set subset in X is closed. So let A be the let A be the single point set in X. So we have to prove A is closed, and it suffices to prove A closure is A itself. So we will prove that A closure is A. Now we have A, this singleton x naught, which is contained in X. So this x naught will be a point in x naught. Now let us pick any point x in X different from x naught. So let x be any point in X different from x naught. Now this by hypothesis this X is a Hausdroff space, so we can separate these two distinct points by open set, say U and V. So then there exists open sets, say U and V, containing x naught, so this is U, this is V, containing x naught and x respectively, so such that their intersection is empty. So if this intersection is empty, now this x naught is equal to the set A itself, so this implies now x naught being an element of U means A is contained in U, because A is a singleton set. So this implies this A intersection V is also empty. So note that a point x in X will be a limit point of A if for any open set V which contain this X has a non-empty intersection with A. I mean so let us write this here. So we have A here and X, any point in X, then we call X this X, we call this X to be a limit point of A if any open set V which contain this X contains a point from A different than X itself. So if this is the case, then we call this X to be a limit point. So this must be true for any open set, but here we have an open set V which contain this which is contained in V and has an empty intersection with A. That means this X cannot be a limit point of A. So therefore X cannot be a limit point of A because of this reason, because we have found an open set V which has an empty intersection with A. So this X cannot be a limit point of A. So hence we know this X is not in A because A is itself to be equal to the x naught, and we have assumed at the first place that these 2 points are different, so this X cannot be equal to A. Also we have proved this X is not in the is not a limit point of A, hence X cannot be in the derived set. So hence this means this X cannot be in the closure of A. So hence X can not be in the closure of A. Now this X was chosen arbitrarily. That means no point in X will be other than X on, I mean, can be in the closure of A. So since X was chosen arbitrarily, so hence X cannot be in the closure of A for all X not equal to X naught in X. That is, the closure of A is A itself, because this A prime is empty. Therefore A closure means A union A prime, which is A union empty set, and that is A. So hence A is closed. Now suppose A is the finite set, say x1 x2 through xn, so it's the finite subset of x. Now what we had to prove? We had to prove A is closed. Then we can write this A as a union of singletons. So this is I runs from 1 to n. Or we can write A complement to be the, so using De Morgan's law, this is the, because A union B complement is actually A complement intersection B complement, so this is going to be the complement of the singletons. Now we know that I mean, so one can note here each singleton xi is open in x, then the xi complement will be an open set in x, and this A complement is finite intersection of open sets, hence A complement is open, that means A is closed. So since each singleton is closed, since each singleton, say x sub I, is closed, then xi complement is open in x. So this is closed in x, so this is open in x. Now x being a topological space means this x is closed, I mean the topology on x is closed under finite intersections. So hence A complement is open because our topological space xt is closed under finite intersections. So since T is closed under finite intersections, so therefore this A complement is open and hence A is closed.